We use them constantly. You might be using one right now to watch this video. But did you know that touchscreens, like the one on your smartphone or tablet, rely on the electrical impulses in your body to function? If you've ever been to the hospital, you probably remember that annoying beeping screen in the corner of the room. You know, the one that makes sure you're still alive. Well, that machine is hooked up to your heart, which sends electric impulses through your body when it beats. Yep, your body is electric. More on that later. Touchscreens are alive with electrical impulses, and every time you use a touchscreen, you are bringing them into contact with the electrical impulses in your body. First, let's take a look at the electrical impulses in a touchscreen. The touchscreen used in an iPhone is called a capacitive touchscreen. If we were to turn that iPad on its side and zoom in, this is what we'd find. On the top, a layer made of conductive electrodes. In the middle, a gap filled with air needed for insulation. On the bottom, a second layer of conductive electrodes. An electric sandwich, you might say. But why does it need to be a sandwich? Can a touchscreen just have one electrified layer? The short answer is no. A touchscreen needs current to flow between one layer and the next so that the stimulus from our fingers and the stimulus from the iPad can interact. So that's cool, but how does a touchscreen device know when you're touching it? Let's get back to the electric impulses in the human body. Just like the touchscreen, which relies on two layers to transfer electric impulses back and forth across an air gap in the middle, human cells transfer electricity across the cell membrane. The inside and the outside of this cell are both solutions of various salts in water. As opposed to the cell membrane, salt water constitutes quite a good conductor because there are free ions that can transport electrical charges. What we have then is two conductors, the inside and the outside of the cell, separated by an insulator, the membrane. This makes it possible to have different amounts of electrical charges inside and outside the cell. When some of the negatively charged particles leave the cell, they change the electric charge, kind of like flipping a switch, and this creates an electric impulse. Like a human cell, the conductive layers of an iPad, they're covered in electrodes, deliver a charge from one layer to another. So, when we touch the screen with our finger, we're bringing the electrical current in our body into contact with the current in the device. The thought of electricity passing through your body every time you send a text freak you out a bit? Fret not. The currents that flow through touchscreen devices are within the electricity levels our bodies generate naturally. So that, my friends, is how a touchscreen works.
Touchscreens are everywhere. Not just in smartphones, but in supermarkets, ATMs, and even airplane seats. And you may have noticed that not all touchscreens are the same. The old school touchscreens can be pretty tough to use. Sometimes it feels more like a push really hard screen instead of a touch screen. On the other hand, certain smartphones and computer monitors are really responsive to many different touch patterns. There are lots of different technologies out there, but they're all trying to achieve the same goal, sending precise electrical signals from specific locations on the screen. One of the most widely used types is resistive touchscreen, where you have to physically push and bend the screen to make it work. Resistive touchscreens are made of two separate layers. The top layer is made from a flexible, transparent material such as polyethylene, which is a common plastic used to make things like soda bottles. And the bottom layer is made of something more rigid, like a sheet of glass. To make the screen work, both of these layers are thinly coated with some sort of metal compound that conducts electricity, like indium tin oxide, which is commonly used because it's transparent. These layers are also separated by tiny insulating dots called spacers, which don't conduct electricity. They keep the screens apart to make sure there aren't any false touch signals. When the screen is on, a small voltage is applied across the screen in both horizontal and vertical directions. As soon as you push down on the flexible screen with anything, like your finger or a stylus, it connects the two layers together. This changes the voltage, and a small processor connected to the screen can calculate exactly where you pressed in X and Y coordinates. These resistive touchscreens are pretty affordable and durable, so they're used for things like credit card readers in grocery stores where you need to capture touch data of a messy signature over and over again. But they can be a little frustrating to use if you don't push hard enough. Plus, they normally can't understand multiple touches at the same time, so they're no good for two-finger zoom or more complex tasks. That's why, these days, most smartphones rely on capacitive touchscreens, where your finger becomes a key part of the electronics. There are different kinds of capacitive touchscreens, and they can vary from device to device. But one basic design is a sheet of glass containing a grid of hair-thin lines of a conductive metal, like indium tin oxide. The grid lines in one direction are called the driving lines, which provide a constant electric current, and the lines in the other direction are called the sensing lines, and detect this electric current. At every point where the sensing lines and driving lines cross, there's a specific electrostatic field, which is registered as neutral by the processor in your smartphone or computer. But that all changes when something conductive comes along and touches it. Like your finger. See, the human body has a natural capacitance, which means our bodies can conduct electric current and can store electric charge. So when your finger touches the screen, the charge in the screen is drawn around that point, distorting the electrostatic field. The electricity doesn't actually flow through your finger. The electrostatic field feels the effects of your electric charge and redistributes itself accordingly. Even really small changes are detected by the processor, which can then interpret the patterns you're making, whether it's a tap or a slide. Because the lines of the grid are so thin, capacitive touchscreens are super accurate, and some versions can process multiple touches at a time.